So thanks for the nice introduction. So I'm going to be talking about active liquid crystals in the liquid crystals program, which I guess, and of course, there's a program which has active in its title, which has just started. So I think the same might be of interest to both communities. This is work mostly done by a former student in Paris, a current student, and some collaborators of mine. And the people at the bottom gave them money. So I'm going to sort of want to set up the scene by talking a little about active matter. Is there a pointer for? Yeah, that's okay. Okay. Better. Start again. Okay, so I want to start off with giving my edition of active matter, and I want to say something about maybe making the link with microscopic behavior and macroscopic behavior. So I want to talk about the way we do it. There are, of course, many ways of doing that, and then I will probably have only time to talk about one of these two, so we can have a vote of which one we want to talk about when we get there, and then I'll finish off with an outlook. So, active matter. Well, what is it? Well, what I say is that it's some set of elements which are driven at an elemental level. So each of these elements is driven. So it's a system that's out of equilibrium. And so that's maybe not so surprising. We study out of equilibrium systems all the time. But they're interesting because the out of equilibrium effect is a bulk effect. It's not something that's coming from the boundaries as we are used to thinking. And that has interesting implications. And the other thing that I'm going to look at, in the system I'm going to look at, is that the units which are active are orientable. So that means that they can form states which have some orientational order. And then I want to add the word soft. And what I mean soft, I mean that I'm interested in, so you could think about it, I showed pictures of flocks and shoals, which are all very interesting, but I don't want to talk about those kinds of active systems. I want to talk about systems which are a bit smaller. One, because that's the background I come from, and two, because maybe they're simpler. And so maybe I can try to extract some simple ideas from studying these systems. Who knows, they may be useful for the other systems, but I'm not holding my breath. Okay, so the active elements I'm going to talk about today are going to be elements which are small. So they're typically of the order of a micron. And the activity that's driving them is going to be weak. So therefore, I mean, I don't have to worry about fluctuations. And the dynamics is slow. So those are the things that we want to bear in mind. And these elements are the sort of things that people who work in soft matter are used to thinking about. Okay? So let's look at some examples. So sort of one example system would be the cytoskeleton. So I've got cytoskeletal filaments. So these are, for our purposes, these are relatively rigid rods. They are polar, which means that the things which they're made up of have a sense of a head and tail. so that these objects can be I'm going to associate an arrow with these objects. And they interact with a bunch of other proteins. The ones which are of particular interest to me are the molecular motors, which convert ATP into mechanical work by interacting with these filaments. And more or less, we could think about them walking along these filaments in one sense, determined by the arrow. And now, what you could say is the one thing, interesting experiment you could do is, let's say, what happens when I put a bunch of such filaments together. So, for example, I could prepare a slide and then I coat it with motors, and I put the filaments on top. So the filaments are driven by the motor, so they walk. So that's, that's fine. That sounds reasonable. Then we can put lots of them together and start increasing the concentration. And then when you do that, you start seeing a variety of interesting patterns forming. So for example, here we can see waves of high density regions interspersed by low density regions. You can formation of spontaneous dynamic structures, which my video will not. And what we'd like to understand, unfortunately the video is not working, what we'd like to understand is, can we understand how these patterns emerge based on how the individual elements are driven? Another active element is a self-propelled micron-sized swimmer. So there are various biological examples. And again, we could concentrate this system, have a lot of them at high density, and see what happens. And again, we see the formation of collectively moving sections of these objects, forming rather complex patterns. Okay. So let's look at these pictures here. So what we have here are the color scheme of the arrows is showing essentially the direction of which these things are moving. So we can see essentially sections of these objects moving in some coherent way. So again, can we understand how this behavior emerges from the individual behavior of the elements? Okay. So the goal is we want to understand how a large number of these things behave. So we need to decide, since we have such a large number of system objects, it's a very complicated system, we're going to have to decide what things we want to look at. So we want to essentially identify some large-scale degrees of freedom. And now, one thing we can look at are measures of liquid crystalline order. So for example, do they align in a polar fashion or do they align in a nematic fashion? And you could obtain a sort of generic model of possible behaviors by using very general arguments based on symmetry and just writing down some coarse-grained model and then studying its implications. But you might also want to be able to relate the properties of the ingredients to the macroscopic properties. So we've got some building blocks, and we want to build the USS Enterprise. And in order to do that, we're going to have to make some simplifications to make this process tractable. And I want to tell you about some stuff that we've done doing that. And the program we're going to use is we're going to start off with some simple models for these micron-sized driven objects. And then we want to have some simplified physical theory which we can extract from that, which links this behavior to macro behavior. And we want to understand the macroscopic behavior. And essentially, mostly what I'm going to talk about is going to be qualitative, but the point is that this framework allows you to eventually maybe say something quantitative. Okay, so now let's go back to our active elements. So we said we have these elements, they are somehow driven. I could put a little arrow on them. And then you might ask the question, can these objects spontaneously organize in some liquid crystalline phase without steric interactions? So now, since we've got these things have heads and tails, we could think of two types of liquid crystalline phases. You could think of a phase where all the heads are pointing together, so you've got some polar phase, which looks like the sort of things we saw. So there, we have these, all the arrows point together, or we could have nematic order, where you have just as many arrows pointing in one direction as in the other, but you have broken rotational symmetry. Okay, so that's the goal. So, first question, can we see that? And we're going to take a particular macroscopic model. So let's take the swimmer model. Okay, so let's just take a collection of swimmers. So we have this micron-sized objects in the fluid. So we are going to look at objects which are moving slowly. So we can estimate the Reynolds number. Reynolds number is rather small. So we are going to look at situations where we can ignore inertia. So we're going to solve these objects are moving in a fluid, so which is Stokesian. Now, just to be clear about what's going on here, in this self-driven object, there are no external forces because it's being driven, driving itself. So what does that mean? So maybe we can see that best by considering sedimenting colloids. Imagine you had a colloid dropping in a fluid. Then you know that in this regime, I calculate the force in it by integrating the stress tensor on the surface, and that stress tensor must equal what the external force applied to this object is. For my self-driven object, there are no external forces. Well, if it wasn't sedimenting, it could be if it had the same density as the fluid it's moving in. So there are zero total force on the fluid. So that means the integral of the stress tensor of the boundary of this object is 0. Okay. There is another thing that we need to bear in mind, which is that the Stokes equation is linear, and the swimming is some periodic sequence of shape changes. So in this periodic set of shape changes, if this sequence is symmetric about its middle, then I'll have no net motion. So I need to have some set of sequences which is asymmetric. Okay. So how do we build one of our micron-sized self-propelled objects? We're going to build them by essentially building a collection of point forces on the fluid. So we have our Stokes equation, we have some forces, and our object will be parameterized by the distribution of these point forces. And in order to build the flow field defined by the object, we're going to use the Green's functions for the Stokes equation, which is the Oseen tensor. Okay. So now there's one more thing, which is that a lot of the experiments that a lot of the things I talked about to motivate my problem were based on studying in the thin film geometry. So in actual fact, the problem that we really want to solve is a problem of a viscous sheet which is surrounded by less viscous fluid. So you could so we would have again our force balance in the plane, which would be Stokes in plane Stokes-like equation. It's coupled to the fluid above and below. We're going to assume it's incompressible, and we have the force balance out of the plane, and we have the relevant boundary conditions which couple the fluid in the plane to the fluid out of the plane. And we can again do the same thing. We can calculate the Green's function for this object, and it is a tensor as well, and it has certain properties. On large, we can define a length scale, which is given by the ratio of the two viscosities.
Why is that a length scale?
Okay, good question. So this one of them is a two-dimensional viscosity, other one is a three-dimensional viscosity. So on length scales small compared to this, the dissipation is in plane, kind of reasonable, whilst length scales large compared to that, the dissipation is in the bulk. And so we can compare what happens in the film to what happens in the bulk. So if you have a fluid of bulk viscosity, then and I have a sphere moving through it, I have a Stokes drag. If I have an object moving in this film, I'll have a drag which depends on this length scale and the viscosity in the plane. For a point force at the origin, I'll have the Oseen tensor for the bulk equation. In the thin film, I'll have this tensor, which I can look at in the two regimes. In the short length scales, it looks like it's logarithmic, it's 2D-like, whilst in long length scales, it goes like 1 over r, so it dissipates in the bulk. So that's kind of what we need to bear in mind. So now, based on that now, we can now make simple models of a swimmer, which we can then put together and to study the collective behavior. So, and the two things we need to bear in mind are the total force applied on the fluid is 0, and that this cycle is non-reciprocal, or breaks this time reversal symmetry. And so the swimmer is just something which is moving these point forces around. And remember, the forces added up to 0. So if we calculated the force density due to one of these objects, the leading term is going to be a dipole. And of course, there'll be higher order terms, whatever it is. But we know that there is no monopole term. So now I'm going to talk about two swimmers that you're going to use to study the collective behavior. So a nice, very simple model swimmer is one which is made of 3 beads, which was introduced by Najati and Golestanian. And so you have 2 arms which move in periodic cycles which are out of phase. And again, if we go through the cycle, we'll see that the motion within one cycle breaks this time reversal symmetry. So this object can move, and we can calculate the speed at which it moves related to the speed at which the arms move. So you can relate microscopic internal dynamics to to the speed of the swimmer. And indeed, if you average this force over a cycle, you do indeed find, in fact, that it indeed starts off with a dipole term, and you can actually calculate what the dipole and quadrupole terms are for this object. So you find that the force density, the dipole term and quadrupole term, both go like the square of the maximum of the arm length, and are proportional to the frequency which it moves.
But do the higher order terms off for some reason so they can be ignored? The first 2 are the same order.
No. There's an L.
Yeah.
In front of them. So they fall off like 1 over L. Okay. We can also make these swimmers using more complicated, if you want, dynamics. So an interesting model is a model where we have, instead of having these 3 beads moving in a line, we have the beads constrained to move on a circle and each rotating. And again, it's more or less simple enough, so you can calculate everything. So you can calculate its speed, and you can calculate, for example, its force density. What's interesting here is that the leading term in this swimmer is a quadrupole, so therefore, again, you can calculate that there's a quadrupole term, and it has a certain, it depends on the mean distance between the rotors, and is proportional to the force which on each bead, which can be related to the frequency at which the beads are rotating. Okay, so the main thing we should take here is that we have a model for an individual active element, and we can put those together to look at the collective behavior. And again, I just want to show here the fact that actually this thing clearly breaks time reversal symmetry. So therefore, this thing will move, despite its moving in this very viscous fluid. I just want to note something, which is that we can, if we put in the numbers corresponding to one of these objects moving at sort of the speed of a micron a second, we can calculate the Peclet number, and it's less than 1. So that means that essentially diffusion of this object is important. That's an important point. And we can do the same thing for this 3-bead swimmer. It has the same. If we put an object, if we make certain object which is of the order of a micron in size, the Peclet number is small. So now we have our elements, And now we'd like to understand how they behave collectively. So we have a very complicated driven system. So first thing you'd have to bear in mind, well, I could have any sort of complicated behavior is possible, of course. So we really have to make a number of assumptions. So first assumption is that there's some non-equilibrium steady state which we are close to, where things are not varying very fast. And then we can essentially describe the dynamics of the system using some slow hydrodynamic modes. And then what we want to do is to project this complicated internal dynamics onto these slow modes. Okay. So how do we do that? Well, so I have I have some variable x which could correspond to the positions and orientations of my active elements. I have my driving term, which is coming from the internal dynamics, which is all specified, and I have fluctuations. I'm going to take the fluctuations to be white and Gaussian. And if these velocities of these objects, which would be an angular velocity and a linear velocity, have only a pairwise interactions, which is already an assumption, and we will talk about that in the suite, then I could write my velocity as just an internal velocity, which is the self-driving, which drives one of these objects, and I have some interaction with the others. So I have a bunch of stochastic ODEs, and I can use that to define a density, the probability of finding a particle with some set of variables, and this will satisfy some conservation law. And this conservation law would have three terms. The first term is coming from the driving of one of these objects. The second term comes from the interactions with the others, and hence requires that there is a two-particle density, and then there will be some term coming from the fluctuations. Okay. And I can also write down an equation for the two-particle density, which will have a similar form, and of course we have the usual closure problem. And what we're going to do is we're going to use the meaningful approximation where we can write this two-particle density as a product of one-particle densities, which means we're ignoring correlations. So we now have a closed system of equations. We have for this one-particle density. Our rods have positional orientation, and there will be some angular velocity and velocity, which drives their motion. Okay. So the internal, we have already calculated the velocities of a single object. So we just need to calculate how they interact. So for example, let's take the 3-bead swimmer. So we have a bunch of beads with forces on them. So we can write down the the solution to the Stokes equation, which is appropriate to that, and we can calculate the velocity field as a function of the time dependence of the force. And what we'll find, the way we do this is we're going to do an expansion in the separation, the ratio of the size of the objects to the separation, to their separation. So the leading term will be the self-velocity, and then there will be corrections coming from the interactions with the others. Now, these objects swim in a straight line, so we only have a self-velocity, but there will be corrections to the velocity coming from interactions, and also corrections to the angular velocity coming from the interactions. And these effective interactions are mediated by the fluid. So remember that we have a dynamic system. So in order to get this average, we're going to be averaging over a cycle. So we're averaging over one of these cycles. Okay. So in the end, we now have an equation for this density. We have two currents. One current has a diffusive term. It has this internal driving interactions mediated by the fluid. For the rotation, we have a diffusive term, and we have the interactions mediated by the fluid, because the driving does not drive any rotation. And these we have obtained by, of course, calculating the hydrodynamic interactions. Okay, so now we have how a pair of such objects behave, and then that's still not good enough. We still need to simplify. That still has too much information for us, because now we have the probability of finding a particle with a certain position orientation, and what we want to capture is some picture of the local order, how these objects collectively are moving. So we're going to have to course grade. So now, given that we have this polarized or nematic order possible, we can perform a moment expansion of the concentration. So I can calculate the density of particles, which is average over all orientations. I can calculate the mean orientation, the local orientation, which is the average of u, but again over the distribution, and I can calculate a second order tensor which measures nematic alignment. And this boils down to essentially expand. I can expand in general my density in terms of these tensors. We can construct a set of orthogonal tensors which are measuring more and more structure of the solution. And the ones that we're used to thinking about are, of course, the U and this second rank tensor, which give us the polarization in the nematic order. But of course, we could also look at more esoteric types of order in these systems within this framework.
Okay, this is in 2D.
So yes, this is in 2D, yes. So again, let me just recall. So we're doing a coarse graining. We're coarse graining in space and time. So as remember length scales. We have A, which is the size of objects, which is the joint of the force. We have D, which was somehow the amplitude of the internal motion. We have L, which is the size of the object. And then we have R, which is the separation between the objects. And then we also are looking at time scales long compared to the internal cycle. So we're looking again, so we're coarse graining in time as well. Okay, so we've now gone from a model of an individual self-propelled object to a set of equations for these order parameters. So P here would be the moment, the average of U, whilst S was the Q, effective Q tensor. The first thing is let's just ignore gradients. So we're just asking about what does the bulk behavior of the system look like. So what we find is that there's a tendency for rotational diffusion to destroy any kind of coherent motion, and then we have things generated by the driving, which come both from self-driving and from interactions with the other particles. And again, let's take the 3-bead model. So one thing you note if you're taking that model is that the length of the arms is very important to telling you what the average stress distribution looks like. So if the forward arm is longer than the backward arm, then the force dipole that you have is has the forces pointing inwards. If it's the opposite, the dipole has the forces pointing outwards. And if they are equal, then actually you have a quadrupole. So we can actually look at the behavior of the system as we vary this ratio. And so we obtain a phase diagram where the axes are the density of these objects, and then we could define the force dipole sign, where we say positive where the forces are pointing outwards and negative where the forces are pointing inwards. And if the forces are pointing outwards, then we see that there's a transition from an isotropic to a nematic phase, and then furthermore to a polar phase. And actually, it's possible to switch them depending on details of the how the internal dynamics of the arms. So actually, so it is possible to construct internal motion schemes where, in fact, you have a polar phase. So therefore, there is no nematic phase; just it goes straight to a polar phase. However, when you have this puller where these forces are pointing inwards, then the isotropic phase remains stable.
Tanny, I think you may have switched your microphone off just now.
Okay.
It suddenly
The voice
that's
went
better.
down. Okay.
Yeah. It's just it's being recorded. I can hear you without a microphone, but it won't
Okay.
record very well.
Okay. And
Non-ordered phase for the poles.
for the pullers.
So, Tanny, is there an implication that purple line doesn't go over to the left-hand side?
Okay, yeah, so that's, so remember that we have no, I haven't put hardcore interactions in this model. I said, so I'm asking, can you have
Yeah.
order without
Yeah.
hardcore interactions?
Yeah, yeah.
If I had hardcore interactions, of course, then I would have this thing would have there would be an isotropic mesh transition at some density. So this is saying that even if there were no interactions, you would get order. So that's the punchline.
So that purple line shouldn't actually strike the vertical axis.
No, it keeps going up. It keeps going up. Of course, if you included, you could of course introduce hardcore interactions,
Yeah.
and if you introduce hardcore interactions, of course you find that it intersects the axis.
And why? I'm a bit surprised that colours behave in a very different way. So it's sort of where in the analysis does that come in? And I understand about the sign of the velocity field being different.
Let me now wave my arms. So I guess it is really to do with you can look at the flow field close to a puller, and so we now have, so essentially I've got to have something, a flow field which is, well, actually I have a picture I think of one of them, of the flow fields here in a slide. So let me. Okay, I think it's here. What's happening? Okay, well, let's leave it up here. It's not very clear. Let's have a look and see. Okay, so effectively, so now. So here we have these things which are pushing. So here we have our pusher and our puller, and I guess the point is that you can see from the flow field that if I brought one of something which was swimming in the same direction next to it, the flow fields the velocity fields would be at an angle. Whilst here, it is much easier for them to align.
Okay, we took effort.
Okay.
Well, could you explain where you get these phase curves?
Okay. The phase diagram.
Yeah.
Okay. So. Okay. So we're going to do linear stability. So I'm going to look for steady states. I'm going to set the left hand side to 0, and I'm going to look for solutions of this equation for the magnitude of P or S, where P would be the magnitude of the polar order, and S would be the magnitude of this second rank tensor. The trace. And when the beta knots are 0, then essentially I find that my only solution is P is 0. Okay, so and S is 0. So therefore, I can only, so this corresponds to an isotropic state. There's some uniform density, and the amount of order of P is 0, the amount of nematic order is 0. Now, once I have these terms, depending on the signs of these, it's possible for me to find solutions where P has non-zero values. So it's just looking for the steady states of this equation. I find a boundary as a function of density and beta between a state where P and S are identically 0 and a state where P and S have some finite value. I should also note that in the polarized phase, the nematic order parameter is slave to P in some sense. It's just given by this. Okay, and that comes from this equation here.
What is slave to P?
I mean, so imagine that P is non-zero. Okay, so now I get some value of P with whatever it is. Then I've got to solve, this is going to be equal to 0, and this tells me then that S is going to be related to a second rank tensor constructed from P.
I can see it that way round, but the other way round, when P is equal to 0 and you have finite S that is between the red and the purple lines.
Yeah.
Is that obvious from the second equation?
Yeah, so then this is going to be 0.
Yeah.
And then you're going to have this term. And this term is going to, this is the term that's going to drive you.
Right, but I got that term is equal to 0 on the left-hand side, the entire equilibrium.
No, I mean, so I've got the time derivative of this is equal to 0.
Yeah.
So now I'm going to solve this linear equation for S, and I'll find that if beta 1 is positive, then S would be 4 dr over beta 1 times rho naught.
The first.
This is S squared. Thanks.
I see. Okay, yeah.
That's an S squared?
Yeah.
Yes.
Yeah.
Sorry.
No, I'm with you then. Yes.
Yeah.
Sorry, but this is just a linear analysis.
So this is no, it's a bulk analysis. It's non-linear because the equations are non-linear. Because
But then the question is, how can you be sure that you do not break the limits of physical meaning for these parameters?
What do you mean by? I'm not quite sure I understand that.
The eigenvalues, for example, of this S parameter must be bounded.
Yes, I mean they are. So we can check all this a posteriori. So we have all the numbers, so we can just put numbers in and we can just check that the values that you get are reasonable, and they are reasonable. So I mean I don't think you can say I don't think with this type of analysis you can ever the way you justify the solutions is to check if they are physically reasonable.
You don't have any a priori
No.
bound on that.
Yeah. Now, and of course, the reason being that we have done a low density approximation, so we have assumed that the particles are far from each other. So, of course, once you bring them close to each other, you have contribution coming from higher body effects, which we've ignored in this analysis. So, this is a low density expansion. We've expanded the low density. So, this is really only valid, close to the boundary. It's not really valid deep in, let's say, an nematic or polarized phase, because of course you need to have something which is going to saturate your order parameter, which is not in this model. So I guess I just want to, I want to make a point again that if you compare this with the 3D case, in 3D case you don't get any none of this stuff happens, and this is purely because of this two-dimensional hydrodynamics. So in 3D you just find that all the terms cancel. And then we can do so now we've found this bulk behavior, which we got by ignoring variations in the fields. we can now ask, we can do a linear stability analysis to ask about what happens when you allow modulations of the density and the polarization. Okay, so we just put in little modulations of density, polarization in the polar phase. Even with the nematic phase, we would put modulations of the density and the nematic director. Turns out that the density actually in the nematic phase doesn't develop fluctuations, it's always stable. And you can then look at what happens. And so you'll find that there'll be some growth of this wave of these modes with some wave number, and if this thing is positive, then it tells you that fluctuations grow. And so we can look in the homogeneous phase where there's no order, and we find that everything is fine, it behaves more or less like an equilibrium system. And then we can look at the nematic phase or the polar phase, and we find they're both unstable, but in different ways. In the polar phase, there is a coupled density director splay mode. So we get modulations of the polarization, which are coupled to density modulations. And in the nematic phase, there is a director splay mode. So if we recall these modes, these propagating things we saw in the sliding assays, this is consistent with these kinds of instabilities. I kind of just, okay, so I just then want to say something that you can also do, so what we did essentially was we integrated out the fluid. So we integrated out the fluid to get some effective interactions between the particles. But you could actually keep the fluid, so it's possible to do calculation keeping the fluid present. And it's possible then what you find is that the stress tensor develops additional terms. Now these have already been proposed by various authors working in the field of active matter. So these terms are known. It's just that you can relate these terms to properties of the swimmers. So for example, taking the 3-bid swimmer, there is going to be a term which, this is the force dipole term really in the stress tensor, and it has this form, but you also have some gradients in the director which you can also calculate. So, okay. So what shall I do? I can say a bit about this about the cilia, maybe because it's an interesting problem. So I think let me just finish off saying a few brief things about oscillations. So we can use the same framework to look at collective transport by oscillating particles. So, we know. Okay, so cilia are long, active filaments which go through some sort of cycle, and are used by ciliated organisms to swim, like paramecium, but also useful for example, for our mucus in our lungs. And diseases like cystic fibrosis correspond to some defects in the mucus actually, and has really bad effects on quality of life of the people who have it. So we could think of a system with cilia as some kind of a plane with a bunch of oscillating filaments. And okay, so one can get into the details of the biology, but let's just think about let's do again in the same way that we've talked about so far. Let's do a very simple model of a cilia. So it's just a bead close to a plane. Okay? And it's undergoing some dynamics. Now we're in an overdamped limit, so we have some velocity, which is related to some force over some friction, and this force has some dynamics. And we can write down a sort of a generic form for this. So we could have quadratic, linear, quadratic, and cubic terms. I've written them in this way because those of us, if you are familiar with dynamics, this looks like a van der Pol oscillator. So, but one point I should make here is normally when you do the van der Pol oscillator, you have your momentum and position. So here, x is taking the role of momentum in the van der Pol oscillator, whilst f is taking the role of position in the van der Pol oscillator. So it's a slightly off-key van der Pol oscillator, if you wish. Okay, so, but in any case, it has this internal dynamics. I'm going to say something about how I justify that based on some models of what happens inside, but that's all we need to know for now. Okay. So now we can ask about what happens when I have a row of such objects, which are coupled hydrodynamically. So again, we can do the same trick we've done before. We can solve the hydrodynamic equation for a single object. We can solve the hydrodynamic equation for a pair, and then we can try to describe a row of these things by writing down some effective theory which takes into account the internal driving, the hydrodynamic coupling, and the fluctuations. So we have them close, they're close to a wall, so actually the hydrodynamic interaction scales slightly differently. It scales like the height for our squid. And so let's just take a pair of such objects. We have one of these oscillators. It's, again, we're in the overdamped limit, but we have these active forces which have this form, and we have hydrodynamic interactions, and ask what happens. Now, you can have oscillations if you have alpha is 0. Okay, so if alpha was 0, this thing would give you oscillations, and it's possible to. But the fact that you have alpha being non-zero means that the frequency is not slave to the phase. Okay? So that means that in the limit cycle that you obtain, that you have variations of frequency with phase. And that's important. And so you can now ask what happens to if you have two such objects. And you'll find that if you have that alpha term not being 0, then they would they synchronize much faster than if alpha was 0. And the sign of alpha determines whether they synchronize in phase or out of phase. Okay, so we've got a pair. So we find that for a pair, they will synchronize, however, very slowly if alpha is 0, but in phase or out of phase when alpha is non-zero. So then we do our usual trick. We can write down some dynamics for the collection of these objects. We have, again, diffusion, self-driving, hydrodynamic interactions. Our variables now are going to be the phase and the position of the oscillators. And then again, we will have relative velocities, which are related to the relative phases and relative positions. And we can do the same thing. We can project onto the moments, and we can obtain a field density, which will correspond to density, and we have a phase, which would be the average, which would be the local phase of the object. And then we can do the same analysis that we did for the thing. So what we have, we have a continuous symmetry here, because our phase variable is something which has 2 pi periodicity. So we're asking whether or not we break this continuous symmetry. And indeed, we find that we do, only if alpha is bigger than 0. So if alpha was bigger than 0, then they're globally in phase. That means all of them are oscillating together as a rigid sheet. And if alpha was less than 0, then they're locally antiphase. So you have sort of long wavelength. So locally, each pair is out of phase with this neighbor, but you have long wavelength modulations of the phase. And it's so interesting because actually, if you wanted to have something which can propagate fluid, you want long wavelength phase modulations. Because if they oscillated in phase, because of our scallop theorem, nothing would happen. They would just go forward and come back. And then, of course, we solved it, we looked at it numerically, and in fact did see that that was the behavior that we got. Just want to say something about trying to estimate these parameters. So you could do a sort of simple model of this object, where you have a little bead with some motor walking along a filament, and this bead is connected by a spring, and the motor itself is connected by a spring. So if the spring gets stretched, it's going to apply a force, the motor will tend to unbind. So you can study the dynamics of this object, and it will give you an effective equation of motion for this bead, and you can sort of calculate all these things based on the properties of the motor. And indeed, if you have a reasonable model for how the motor, i.e. that if the motor comes off when it falls off, you do indeed find, in fact, that this term alpha is negative. I guess probably I should finish off here. So I talked about how we derive hydrodynamic theories for more microscopic kinetic theories. I talked about an actively driven LC transition, and I talked about the fact that there was instability to these phases, which were highly nonlinear, which we, I guess, don't really understand or can't really characterize exactly. And I said something about the synchronization of oscillators, which I said could be viewed in a very similar way. You could view the synchronization problem as a breaking of a continuous symmetry, and this can happen due to, if you want, long-range hydrodynamic interactions. And of course, there are lots of things you could think of doing with these kinds of systems. We looked at infinite systems which you could model with periodic bounding conditions. The bounding conditions are really going to play an important role. You might have relatively small numbers of particles, so fluctuations are important. So there's an element of how do you modify these hydrodynamic descriptions to take account of fluctuations. So at this point, I'll stop.
Thank you very much, Danny. Is there any further questions that you wish to ask?
I've noticed that in some of your expression KB T, where it comes, temperature.
Okay, so the temperature. Okay, so that I guess you could say, so in the fluctuating term, so we always start off with a Langevin equation for the microscopic degrees of freedom. So the fluctuating term, you could say the diffusion constant, has a portion of the diffusion constant is coming from thermal fluctuations, and then of course that a portion of the diffusion constant is proportional to KT. So if you want, there is a part of the fluctuation which is proportional to KT. But of course there are other parts which would be not, which would be active, and which in fact we do not know how to characterize.
You introduced the term minus alpha NINJ into the stress tensor.
Yeah.
Where does it come from?
I mean, are you asking about the?
I mean, did you just hypothesize, or?
No, we okay. So we calculated. So I mean, so I guess presumably you're talking about.
Active stress.
The active stress term, yes. So so basically, we solved the Stokes. You could write the Stokes equation as a background field, which would be without the interactions, plus some perturbation coming from the interactions. And when you write it that way, you see that indeed there is a term which appears in the terms coming from the interaction, which has the form NINJ, and it actually, and we can calculate it explicitly. So you just calculate it. You take your model for the swimmer, and you just do the average over a cycle, and you can calculate it. So. Okay, so here. Okay. So, so I said, so you have your background field of your flow field. You calculate the perturbation of the background field due to the interactions of the swimmer with the fluid, and this generates you that term. So it's nothing. There's nothing clever about it. It's just
because well, maybe we could discuss it later. But if you, and I'm having difficulty understanding that in terms of, say, a dissipation function that would come from this, or am I picking it up wrongly as a viscous-like effect? Because it violates the second law of thermodynamics if it's a viscous effect.
So first thing is that this is a system which is being driven. So there's energy, we have energy sources. So what do you mean by violating the second law of thermodynamics?
Well, if you write down principal virtual work approach and you construct into that the dissipation function, the rate of dissipation into that, then that term NINJ was discarded by Ericsson.
Yes, I know.
Yeah.
But
so that means that it must be coming from some other internal energy source.
yes,
Okay.
that's what it means. It's coming,
like the additional.
and so and that is. I mean, so in order to keep this, this is we have a viscous fluid.
Yeah.
So in order to keep these things moving, if there was no energy source, they would just stop moving.
So this is coming from a supply of internal energy.
Yes, so there must be I'll put it this way, there must be a source of internal energy in order to have this thing keep moving.
Yeah, I agree entirely with that statement.
Okay, so that, and in fact, we are estimating the amount of that internal energy which is dissipated in the fluid when we calculate this term here.
Okay.
So that's what this is. This is just, of course, some of it will be dissipated as heat,
Yeah.
some of it will be dissipated, okay?
Yeah, there's still a change that's incorporated into a balance
Yes.
of work done at the end of the day.
Yes. So in fact, there is another sum of balance of work done in the system, which we have ignored because
Yeah, that's what I was coming to as a next question, because you have to have another equation.
yes. So of course, I mean, at the end of the day, I believe in the second law, no doubt about it. So therefore, I believe that you can write down, if you wrote down a complete macroscopic theory with all the degrees of freedom in it, then
Yeah, so there's an equation that's absent from what you presented then, that involves that internal energy then.
well, I would say that maybe I'll put it this way: that there are sources of energy which we cannot characterize, but we know they are there. I mean, and so we can ask what is the effect they have on the physics at this scale. But at this scale, I don't think you can say anything except that this is a source of energy. So you have some source of energy which I don't think you can.
I know what you mean. It's like some of the standard textbooks on energy balances, and they don't tell you what E is.
Any further questions? I have one very quick, and I just propose to make a wrong statement, and you correct it. And the wrong statement is, since these, must be wrong, I think, since these, the active stress actually comes from internal balanced forces, should be divergent, which is in general not the case. What is wrong?
So divergence free. I mean, you mean that the
Because the total force, as you said, is zero.
yes.
So if such a total force, if a distribution of these internal forces, which balance out to zero, is represented by a stress field, which is the active stress, in order to obey this basic constraint that the total force must be zero, this divergence must be zero.
Well, I would say that you could still have. I mean, so what you're saying, I would say, you put it this way: that you have energy flow within the object. So you're not saying that there are no forces anywhere in the object. What you're saying is that there are no. That if I do the integral, okay,
So if I
and that's true here. The integral is indeed zero.
does it mean that if I take a surface and I integrate over the surface, the active stress, I get zero?
Of the whole object, of the whole active element.
Also in the macroscopic equation?
Yeah, I mean, yes, it is, because of course I still have to satisfy Newton's law. So the divergence of the stress is zero, and the stress has all these terms in it. So therefore, the divergence of that is zero. So I'm still, and in fact, the fact that you have to start with a dipole. I mean, this is basically coming from the dipole. Okay, so the term that would, if you had a term which was like a force monopole, then that would correspond to, well, that would mean that the force, you have to have a delta function here. Therefore, you're saying that the gradient of something is a delta function. So
You say that the total stress is divergent free.
yes.
I would have expected the active stress to be divergent free, but of course I'm wrong. No doubt. All right. Is there any further questions? Then lunchtime. Thank you.